Hydrological models. We use them to predict floods and droughts, to predict the impact of policy changes we're considering, or the impact of climate change. Hydrological models contain the knowledge that we have on the processes that happen on the Earth, on the surface and the subsurface, and how it reacts to water. While that knowledge is ultimately gained from analyzing data collected by field hydrologists, the actual models are made by hydrologists sitting in offices or, for the last year and a half, in lockdown in rooms like this one. Many of these hydrological models exist. Some are regional, some are global, some are simple, some are highly complex. But what is common in all of these models is that it's very hard to get the model that someone else built to run on your computer and build upon it. And this problem hinders collaboration between hydrologists. I am Rolf Hut. I'm an associate professor at Delft University of Technology, and together with a team at Delft and at the Netherlands eScience Center, and with input from the wider hydrological community, we have designed and built the eWaterCycle platform. The eWaterCycle platform is designed to take away the barriers that hinder us to work together and build upon each other's results. By working online, we make sure hydrologists don't have to install software on their local machines or be dependent on local versions of operating systems, programming languages, or supporting libraries. By working with container technology, we have found a way where we can interact with an existing model without having to look at the code of that existing model. We can even design an experiment in one programming language while interacting with a model in another programming language. Models including PCR Globe WB, WFlow, and ListFlood are currently supported by the eWaterCycle platform, with more to be added in the future. There's even an option for hydrologists to contribute their own model to the bigger collection of models available in the eWaterCycle platform. We've built a pre-processing workflow that splits pre-processing up in a part that's only dependent on the forcing dataset chosen and a part that's only dependent on the model. In this way, if a new forcing dataset is added to the collection of available forcing dataset, it immediately becomes available for all models already in eWaterCycle, and the other way around, if a model is added, it can start to work with already incorporated forcing datasets. Currently, ERA 5 and ERA Interim are supported, and the way this is set up, it's relatively easy to add new datasets to this collection. In this video, I will explain what the eWaterCycle platform is and how hydrologists can use it in their research. I will show some typical examples of research that can be done on the platform to showcase what the platform is capable of. For system administrators that want to install the eWaterCycle platform on their own infrastructure and provide it to their own users, the hydrologists that they work with, there's a separate section of the documentation that explains how to install the entire eWaterCycle platform on your own infrastructure. There's a link in the description of this video. The eWaterCycle platform provides an online environment where hydrologists can do their computational hydrological research. The front end of eWaterCycle that hydrologists will experience consists of two main components. An explorer, where hydrologists can browse and select models or example experiments. A Jupyter environment, where these experiments are subsequently run, where they can be changed or where they can be built upon, or where completely new experiments can be built from scratch. This is what the explorer looks like. In the explorer, hydrologists can browse the available models in eWaterCycle. They will be projected on a map because most of these are defined for certain regions. They get parameters set for certain regions or calibrated for certain regions. The models available are PCR Globe WB, WFlow, and the M1 version of Marmot, which is a very simple single bucket model, just to showcase that we can work with that as well. For example, if we go to WFlow, we see a number of regions for which WFlow is available, and we can add, for example, the Meuse to the map, and we will get information on WFlow for the Meuse. If we click on that, we get the name of the model, the name of the parameter set, which forcing is used, and which observation is used to compare it against, because we can start an experiment, and this experiment will start up a Jupyter environment where a notebook is generated from this information to make sure that we can run a very first experiment to show what you can do with WFlow. Let's do that. I click Start Experiment, and then it opens a new tab with a Jupyter environment. And for this video I've already run this notebook, and if we scroll we see it loads the parameter sets, it loads forcing data, it sets up the models, it loads observational data, in this case from GRDC, it subsequently runs the model, and as analysis it plots a hydrograph of the observations and the model run. By providing users with a notebook instead of just the hydrograph, we give them an environment where they can start building upon it and can start doing their own experiments. If we go back to the Explorer, we see that there's also a few example notebooks and tech paper notebooks. These are the notebooks that are discussed in the paper The eWaterCycle Platform for Open and Fair Hydrological Collaboration, which is currently under review in GMD. These notebooks contain experiments that showcase what can be done as type of experiments on the platform, and I will go through a few of these to also in this video explain what the kind of experiments is that you can do on the eWaterCycle platform. If you press this button, it will open again a Jupyter environment, this one, where 5 notebooks are presented. The first one is again a Hello World notebook. In this case we're running the Hello World. We generate a hydrograph for the Marmot model, but we're also generating the forcing data required for it. And what I want to stress here is how you create a model, which is done in this line. You just simply say, I need a model object from the eWaterCycle collection of models. Give me a Marmot model, and this is the version that I want, and I want to run it with this forcing data set that I just selected. That model then needs to be set up and initialized. Setting up a model generates a configuration file. Most hydrological models need configuration files to run. By splitting this, we make sure that if you're an expert user and you want to change something in the configuration file, you can still do that. For this simple use case, we're not changing the configuration file. We just basically run the model, which is done here in this loop. We basically say while the time of the model is not yet the end time of the model, we just update it every time step, which sends a signal from this Jupyter environment to the container that's running somewhere where the model is in. Please do one time step. At the end of the time step, we ask the model get value discharge, so that we can store the amount of discharge calculated by this model in a array that we're building. And then we can make a plot of the discharge that we calculated, and we can compare it again with observations for the same basin, which results in a hydrograph. Of course, this is running a one bucket model for a very big and complex catchment. We could expect that this would not result in a very good hydrograph. To compare this, we have a second use case where we're using 2 very complex models, WFlow and ListFlood. And the WFlow model is developed by Deltares. It's a very complex model. It's distributed. It requires a lot of input files. But what I want to stress is that running WFlow within the eWaterCycle platform has about the same code that it takes for running the Marmot model. It's still just saying I need a model object. In this case, I need a WFlow model object. Running this piece of code will start up a container that contains WFlow and that you can talk to. In this experiment, we're doing 2 models. We get WFlow and ListFlood, so we can compare which of these has, for the purpose of our research, the best performance. In this case, we're just putting 2 models next to each other. What we often want to do is have models coupled or interact with each other. That's tackled in a third use case. In this use case, we're using the PCR-GLOB WB model to run the Rhine basin, but we have expertly cut out the Moselle sub-catchment, and we're running the Moselle as a single bucket model in Marmot again. We're picking these 2 models because PCR-GLOB is written in Python, Marmot is written in MATLAB. Actually, we're running Octave, the open source version of MATLAB. So we can couple a MATLAB model and a Python model from a Jupyter environment. It will look something like this. Here we run the experiment. We have created an experiment model object and we have created a reference model object. The reference will run the Rhine without interfering, without cutting the Moselle out, no interaction with Marmot, and the experiment will be the one where we do the coupling. We just run the reference model normally. We run the Marmot model normally, but then we take the discharge from Marmot and we say the amount of water we want to add to PCR-Glob is the discharge from Marmot. The current value in PCR-Glob we can get using the getValueAtCoordinates command. And then we can say what is the amount of water that we want to put from Marmot into PCR-Glob. So we can say the value to set in PCR-Glob is the water that we have to add plus the current version. And then we can use the setValueAtCoordinates command to say to the model, here is an amount of water, please put it on this variable. It will now have this value. And in this way, you can interact with the state of the model from the Jupyter experimental environment without having to go into the code of the model. Then we run the experimental model, and then ultimately we collect all the data to see what the effect is of the discharge calculated by PCR-Glob when this catchment has been cut out. And here we can see the resulting hydrograph where we show the observations, we show the reference model, and we show the experimental model where we've combined two models in different programming languages. All the examples I've shown so far have mainly been using the output of models, and in one case inputting the output of model into another model. Sometimes you want to interact with the state of a model, and that's what I show in the final example in this video. In this case we're using PCR-Glob again, and now we want to say PCR-Glob calculates evaporation at every time step. What if we want to correct the calculated evaporation based on observations we have from FluxNet? What we do here in the running of the model is we still say while the time of the experiment is not yet the end time, we update the experimental model object that we've now created, and then we say we apply FluxNet correction, which is a function, and it takes in the entire model as an argument, and it takes in FluxNet observations as an argument. This function is something that we have written and is defined up here, apply FluxNet correction. And what it does is it takes a model in our case the experiment, and data, and it starts by getting all of these important hydrological values out of the model using the getValue commands. And then it starts to calculate what evaporation was and what it should be changed into to ultimately, here at the end, set the value of both channel storage, the amount of water in the channel, and upper soil storage, the amount of water in the soil. So based on FluxNet evaporation, we can correct the state of PCR-Glob during runtime. And by having this as a function on the Jupyter part, we can clearly separate the model and the experiment we want to run on the model, while still interacting with that model and interacting with its state. The result is a hydrograph where we again have a reference and an experiment. A reference is where we don't do the updating by FluxNet data, and the experiment is where we do, and we compare it again to GRDC observation data. And what I want to stress here is that this experiment is the result of the bachelor thesis of a bachelor student in hydrology, which means that by providing this platform to the hydrological community, this type of research where you can directly interact in the state of a highly complex model is now available to bachelor level students. And this shows, in my opinion, that we can start building upon each other's results with greater ease, that we can start collaborating with greater ease. With these example experiments, I have shown what the water cycle platform is and how hydrologists can use it to do their research. Currently, the water cycle platform is running on demonstration infrastructure provided by SURF. Depending on future funding streams, we hope to provide an online environment where the entire hydrological community can actually work together, build upon each other's result in a stable environment that will last for more than demonstration infrastructure. But that funding stream is currently being requested. If you want to work now with the water cycle platform, there are a few options available. If you have access to high-end infrastructure, then you can ask your system provider, your system administrator, to install the eWater Cycle platform on your infrastructure. There are detailed instructions provided in the documentation of the eWater Cycle platform on how to do that. The link is provided with this video. If you don't have access to that kind of infrastructure, you can get in touch with the team that's built eWaterCycle. Details are provided with this video or with the accompanying paper in GMD, where you can say that you want to work together with us, and we can see if we can facilitate that, which of course depends on future funding streams, but we're working hard to acquire these, as most scientists are. I have explained what the eWaterCycle platform is and how we can come together. By introducing the eWaterCycle platform to the hydrological community, we hope to break down technological barriers so that we can truly build upon each other's results, work with each other to further the hydrological sciences.